Yeah, it's still not up at my end.
It is showing a recording started, I think.
Yeah, somehow in my screen doesn't. But I think we're good to go. Please go ahead. Thank you.
Okay. Thank you, Dr. Kalyan. So welcome everyone to the last day, session 1. So let me switch off my camera and share my screen, and then I'll start. I hope my screen is visible.
Yes.
Okay. Okay. So in my first part, I have discussed about the possible attack on main memory, uh, the row hammer attack that can flip a bit in the adjacent rows. So that row hammer attack I've explained in my first part, and then second part, uh, as I have already mentioned, that I'll discuss about the cache memories and NOCs. So mainly the on-chip components, because if we see the components of memory, then main memory is a off-chip component, but cache memory and the NOC components are on-chip. That means they are embedded within the processor chip. Okay. The today's talk, the theme of today's present talk is little different from the from my last talk, because I have promised in my first talk that I'll try to give you some starting point from where if anyone is interested doing research in this area, then he or she can start. So that's why in this talk, I'll discuss about different possible attacks. So it's not just I may not go in detail of a particular attack, but I'll discuss about different possibilities of attack. That what are the attacks possible in cache memories and main memories. And that's why I have given another name to my talk today: the Million Ways to Attack a Memory. Why? Because there is a Hollywood movie called Million Ways to Die in the West. So in the same line, I have given the name of this talk as Million Ways to Attack a Memory. So all the attacks that I will discuss today, some of them may be all are very simple, will be very simple, and all these attacks are already been handled properly. So it may be possible that all the attacks that I'm explaining are not very challenging. They may be simple also, but I'll also explain some attacks. Those are already proposed, and the countermeasures are still people are trying to propose the countermeasures. So there will be some attacks will be in this will be also from this category, and then there will be some attacks which are not proposed. So I'll also discuss the possible attacks which are not yet proposed. So in this not yet category, there are two types. One category is that the possibility is experimented by us, or me or my group has already experimented that, and we by experimentally we found that okay, this type of attacks are possible. So I'll discuss this type of possibilities, and I'll also discuss some possibility which are not experimented by me, but I'll only discuss based on my experience that this type of attacks are possible. Okay, so there are different types of attacks I'll discuss, but the most important point here is any of this attack that I'll explain today, I'll only explain it at the upper level. If you want to work on a particular attack, then you have to understand it and you have to spend some time on the attack. Okay, so this slide is from the part one. That's I have written outline and prerequisite from part one. So in part one, I have mentioned that this part I will discuss in today's presentation. Okay, and the knowledge required is basic concept of computer architecture and the previous lectures of FTP. I already mentioned in my last part that you should watch all the previous FDPs to understand this lecture. But yes, I'll today also I'll try to cover the basics. But if you already know the basic of cache replacement policy, partitioning, prefetching, and the basics of NOC, then it will be easy for me. But still, I'll try to cover the basic, but not in more detail. Okay. So this slide was already there in my first talk. Then I have categorized the attack in three category. Attack to steal some secret information. So I've given a name now. This attack I'll call as secret stealing attack. Then side channel and covert channel attacks fall in this category. I think side channel is already discussed yesterday in 2 talks. So side channel is already clear. Maybe covert channel is already. I think it's also discussed covert channel, but I will discuss covert channel in more detail today. So say secret stealing attack, and then performance attack. Performance attacks are mainly the attack which degrade or which degrade the performance of the system. So this type of attack I'll mention as performance attack. And data corruption attack, like row hammer attack, it corrupt the data. So that's why I'll say it as data corruption attack. And I'll discuss some more attack today based on hardware Trojan, which can also categorize as data corruption attack. So I hope you will remember these 3 categories: secret stealing attack, performance attack, and data corruption attack. And how to handle such attacks, detection and mitigation, that I will explain. Then possible research detection, that is either you can propose a new attack or you can propose the countermeasures that I have already discussed in my last talk. Yes, but in today's talk, as I have said, it's mainly based on attack. So I'll try to explain the different possibilities of attack, but I'll also discuss about the mitigation and countermeasure. But that part will be less. I'll discuss, but for countermeasure part, I'll discuss less. More, I'll discuss about the attack possibilities. Okay. So these are the groups here, architecture group of IIT Ropar. If you want to contact any of us, then you can contact. We all work on hardware security and computer architecture. So I'm not spending much time on this slide. So this is the new slide for today's presentation. So I'll start with cache replacement policy. It's not like that I'll explain the basics of cache replacement policy. From now onwards, each and every slide what I am presenting here, I'll explain some basics, some background, and then I'll explain the possible attack that on this microarchitecture. So cache replacement policy. Okay, so before moving forward, I think I should explain this diagram, because this diagram I'll use in my entire presentation here. So this is a set associated cache. Yeah. Okay. So this is a set associative. Cache. These are called set. Basically, the rows are called set, and these ways are called columns. I think I have explained it also in last lecture. So this is a core, and each core has a L1 cache, and there is a L2 cache also here. So we have to the L1 cache is also a set associative cache, but I'm not showing it here because most of the example or experiment that I'll show today is based on last level cache. That's why I'm only zooming the last level cache as set associative cache. But you have to understand that L1 is also a set associative cache. Now, what is the main property of set associative cache is, if you want to place a block in this set associative cache, then first of all you have to find a set, that in which set means row, again I'm saying, in which set the block can map. So in this example, most of the time I'll target only a particular set. Assume that what are the blocks I'll take today all maps to the first set 1. So let me consider that this C1 is requesting for block A, B, C, D, E, F, G, H, like this. So these are the blocks that core is requesting. So assume that it is requesting first time. So obviously there will be a miss in L1. So it will come to L2, and there will be a miss in L2. So it will go to main memory, and then from main memory it will fetch the blocks. So first, suppose A will be fetched, then B, then C, then D, then E, then F, then G, then H. Okay. Now after this, if now if C1 is requesting for a block called K, and assume that all the blocks that I'm requesting are mapping to the same set. So now in this case, when the core will request for K, there is no space in set 1 to place the newly requested block. So in that case, we have to remove a existing block. So that is called cache replacement policy, and it is local to each set. So if we go for LRU replacement policy, then we always remove the oldest block. Why I'm discussing LRU first? Because it is well known. So we'll remove the oldest one. So if you see the diagram here, example, which one is oldest? I think A is oldest. So in this case, what I will do, I'll remove this A, and in place of A, I'll place K. Okay, but let me change this example a little bit. Suppose this C1 is requesting like this: A, B, C, D, E, F, G, H, then again A. If it requests again A here, then what will happen? There will be a hit for A in last level cache in L2, right? And now after this, if it's request for K, then what will happen? In that case, do you think that we should remove A and place K? Any guess? Okay. So see, in this case, we will not remove A to place K, because in this case, we have to remove B, because B is the oldest, not A is the oldest. A is now the youngest block, because we have accessed the A here in this position again. So in a replacement policy, there are three important points. First, insertion, then promotion, and eviction. Insertion means when you are fetching a block first time from the memory, which position you will place it. So normally in LRU, when we fetch a block first time, then we normally place it in the MRU position, or we mark it as the youngest block. This is called insertion position, where you want to insert it. Promotion policy. Promotion means whenever there is a hit in the cache, in this case, this is the case for block A. So if there is a hit in the cache, so how you will promote it? So normally in LRU replacement policy, promotion is from is directly to MRU. Means every time if there is a hit in the cache, we will mark it as the youngest block in the cache. So this is called promotion policy. And eviction policy. Eviction policy means which block you will evict. So in LRU, eviction policy follows evict the oldest block. So for every replacement policy, you have to understand these three modules: insertion, where to insert when the first time a block is coming; promotion, where to promote the block if there is a hit in the cache; and the eviction, that which block need to be evicted to place a new block in the cache. Okay, so this is called LRU replacement policy. And there is another replacement policy called optimal replacement policy that is well known, proposed in 1966. So optimal replacement policy says every time whenever you want to evict a block, so you have to choose a block which will be reused in the farthest future. Means in the farthest future, the block which will be reused, replace that block or choose that block as a victim. So, but we all know that that is a theoretical replacement policy, because no one knows future. No one knows future, and we cannot implement it in a real machine. So that's why optimal replacement policy is not. It's only a theoretical policy, but it's the optimal policy. And still, all the replacement policy that exist in the literature has a difference, performance gap between optimal replacement policy and the all physical replacement, actual replacement policies. Okay, now suppose if we have two code like this. So in a processor, there are two cores. Instead of one core, there are two cores, C1 and C2. Both have their own private L1 cache, and then sharing a common large size last level cache or L2 cache. And now assume that C2 is requesting for blocks like this: small a, small b, small c, small d, small a, like this. And these blocks are also mapping to set 1 only. So now assume that here in this set, the blocks will not be from one application. The blocks will be mapped from the application running in C1 and application running in C2. Maybe it will be a mix like this: A, B, then small a, small c, capital E, then maybe D, then maybe F, then maybe E. Suppose D, like this. It's a mix. Sorry, it's a mix. So, but there is no difficulty of maintaining LRU replacement policy here, right? Because in LLC, we are only maintaining the age, means which one is the oldest, which one is the newest. So Same insertion, promotion, and eviction policy of LRU can be maintained here also. There is no problem. So now a possible attack. So every slide I'll discuss some possible attack here. So what is a possible attack? What is the attack possible here? That suppose the application that are running in C1 and C2, these application knows, or suppose the attacker is running an application. So instead of saying attacker running an application, I will say only attacker. So you have to assume that attacker is an application. So suppose attacker knows the internal mapping, that it is using LRU replacement policy, it knows the internal mapping, how it is mapping to a particular set, then what it can do, that one attacker application will request, every time it will request for a new block, suppose. So A, B, C, D, E, F, G, H, I, J, K, every time it will request for a new block. So if it do this, then what will happen? So this set will be completely filled with only with the blocks of application 1, right? Suppose application 1 is running here, or it's the attacker application. So it means that the attacker application may remove the important blocks of another application, right? So these type of applications are called actually scanning application or streaming application, because it is every time it is requesting for a new block. I hope you are understanding that if every time it's request for a new block, then it means that no matter how big your cache size is, it is not giving benefit to that application. But here benefit is not important. Assume that streaming application is the attacker application, so it is trying to degrade the performance of other applications. So this is a possible attack, but this is a very simple attack, as I said, because it is already resolved. Why? Because see, the paper here I'm saying here, the paper is from 2007, right? Adaptive insertion policy. So next slide I will explain a paper proposed in 2007 which handled this case. It means the attack that I am saying is already resolved, but why I am discussing it here, because such that you will have an idea that what type of attack possible even today. Because what about the new replacement policies? This attack is not possible nowadays in LRU replacement policy, because in 2007 someone has proposed another modified replacement policy. But what about the new replacement policies? If you can understand the mechanism of recent replacement policy, then maybe you can create an attacker application in such a way that it can still misuse or still degrade the performance of other applications. That's why I'm discussing it here. So now let us move to the next slide and try to understand how this scanning application can be handled. Okay, so as I explained that the scanning application are not getting any benefit from cache, because every time it is requesting for new block. So here in scanning application, it is every time whenever suppose this C1 is scanning application. So if C1 is a scanning application, then whenever you are requesting for a block, so what is the insertion policy normally? Insertion policy in LRU is every time we fetch a new block, we put it in the youngest position, that is MRU position. And what is the eviction policy? Eviction policy is removed from the oldest position. So if it is a scanning application, so what we'll do every time, we'll suppose this is I'll redraw the set in such a way that LRU position will be here and MRU position is here. Okay, so now every time we fetch a block, we'll put it here, suppose A. And when we'll remove this block, one by one, slowly, when this block will move from this position to this position, MRU to LRU position, then only will remove this block. It means that these type of block will unnecessarily store in the cache for longer time, and it will block the cache space for other innocent applications, right? So for this type of application, it is better not, when we'll fetch block first time, it is better not to put it in MRU position. Put it in the LRU position first time when you'll fetch. That's just I'm changing the insertion policy. Why? Because this will be used only once. So fetch the block, put it in the LRU position, that's it. So next time when there will be a new request, we have to remove the LRU, so that this LRU block will be removed, A will be removed. So no problem, because this will be used only once, so it is removed. So in case of scanning application, it is better to insert a block in the LRU position instead of the MRU position. Okay, but what about the cache friendly application? In cache friendly application means the application where a block will access or will follow the principle of locality, where a block will be re-accessed multiple times. So in that case, it is better to follow the LRU policy. Means whenever a new replacement block, whenever we have to fetch a new block, it is better to place in MRU position. For example, suppose C2 is a cache-friendly application. So in C2 there is a cache-friendly application running. So if we fetch a block A, then we'll first insert in the MRU position, because we'll assume that these blocks will be re-accessed or re-requested by the core. Okay, but sometimes there may be mixture. Mixture means maybe some applications are scanning, that is fine, but in some case, some application, it is also necessary that sometime it's not necessary that every time all blocks are re-accessed. There may be some blocks which are not accessing. It may be also possible. So there is a solution here. In 2007, they proposed a solution, a new replacement policy. It's called Dynamic Insertion Policy, DIP. It's a LRU based replacement policy. Why I'm saying LRU based? Because promotion and eviction are same as LRU, only insertion is different. How insertion is different? For insertion, they are using two policies. First policy is LRU insertion. LRU insertion means every time you request for a block, we'll insert it in the MRU position. LRU insertion, or maybe I should write it MRU insertion. MRU means every time if you fetch for a block, we'll insert in the MRU position. And what is bimodal insertion? BIP means insert in LRU with high probability and insert in MRU with low probability. This is called BIP. So BIP means every time when you fetch a block and you want to insert it first time in the set, I will with high probability will insert it in the LRU position, and with the low probability will insert it in the MRU position. This is called BIP. So now, if we only go for this MRU insertion policy, this will I think this will help the cache friendly application. And in bimodal insertion policy, when we'll run bimodal insertion policy, in that case, if there is a scanning application, then scanning application will cannot degrade the performance significantly, because most of the block in this policy will be inserted in the LRU position. So what is DIP? DIP is a combination of these two: MRU insertion plus BIP. It's a combination of these two. Why we are saying it's a combination? Because suppose DIP will either run MRU insertion policy, MRU or BIP. Okay, so it's a period. Maybe this is the starting period here. The cache started here. Then maybe for first 10 million cycles, MRU will run, and then for the next 10 million cycle, BIP will run, and then before next 10 million cycle, maybe again MRU will run. So in this way, either MRU or BIP will run. That's why it is called dynamic DIP. It's a combination of MRU and BIP. So now, how it will decide that either MRU should be used or whether MRU should be used or BIP should be used? For this, they use a special data structure. What they use, assume that there are many rows here, many sets here, because here there are only 3 sets I'm showing. Assume that there are multiple sets here, because normally there are more than 1,000 more. I think number of sets is normally more than 1,000 in any cache. So what they will do, they will select some small number of set here, and they will apply MRU here, MRU insertion, and then they will select another small number of set, and then they will apply BIP here. Okay, and this is fixed. Then this small number of sets, first small number of sets, they will apply MRU insertion, and the second small number of sets, they will apply bimodal insertion policy, BIP. And now, after every fixed period of cycle, means maybe after every 10 million cycle, it's the million cycle, they will check the performance, so either the MRU part is giving better performance or BIP part is giving better performance. For example, suppose at this point here, the MRU part is giving better performance, sorry, BIP part is giving better performance. So it means that in the next period, BIP will be applied for the remaining sets. And again, here in this point, again they will check that whether the MRU part or the BIP part is giving better performance. If they found in this position that no, now MRU is giving better performance, for the next period, MRU will be applied to the remaining sets. So this concept is called dynamic set sampling, or DSS. dynamic set sampling or DSS. Why dynamic set sampling? Because we are observing the behavior of a limited number of sets, and then that behavior is applying to the remaining set. Okay, so this is called DSS. So this concept DSS is still used by many replacement policies and partitioning algorithm. So this is a very important point. Even in 2020 or 2021 also, you'll find some paper. They may be working on different direction, but still they use the concept of DSS, dynamic set sampling. Okay, so I hope you understood the concept of DIP, that how it is handling the scanning application, because here it is going for BIP. So BIP can handle scanning application efficiently. But what are the possible attack on top of DIP? So in top of DIP, there may be attack is, suppose the attacker knows which are the DSS set. So this is, as I mentioned here, that some fixed number of set will be allowed and given to MRU insertion, and some fixed number of set will be given to BIP. Suppose this attacker knows which are these those DSS set, then attacker can target those DSS set to change the policy as per his requirement. Maybe when it should go for LRU, it can go for BIP, or when it should go for BIP, the attacker can force it to go according to LRU if attacker knows the DSS set. But as per my understanding, this type of attack is not proposed yet, and I have also not experimented it. Maybe you can explore it, and you can try to find out that if there is a possibility of this type of attack or not. To understand more about DSS, you can read this paper. You will find more about the DSS, that how they apply DSS and all. So this is a possible attack on dynamic insertion policy. It's a replacement policy proposed in 2007. So that's why I'm saying I'm not sure, because the policy is very old. Maybe it's someone has proposed this type of attack, but still you can also work in this area. Then I have written something here in red, that this is also possible for also true for, not from, it's for RRIP. So RRIP is a well-known replacement policy proposed in 2010. Here you can say this is the second reference here is RRIP. But I think, according to me, both DIP and RRIP are almost similar. The basic concept is same. So if this attack is possible in DIP, then the same attack will be is also possible in RRIP. So you can explore this. But again, RRIP is also a old replacement policy. It's proposed in 2010. So I hope you are getting some idea here that what I'm trying to explain. I'm trying to explain that if you know the internal architecture of a replacement policy, then maybe an attacker application can be designed in such a way that it can misuse the replacement policy and degrade the performance. So it may be you can also practice it for the recent replacement policies. For example, in next slide, I'm showing you a replacement policy called Hawkeye. This is a very well-known replacement policy proposed in 2016, I think. So in the Hawkeye, what they do is, in short, if I try to explain, they try to simulate the behavior of an optimal replacement policy. I have explained you what is called optimal replacement policy, and I told you that it is not possible to implement it physically because no one knows the future. But what they did here in Hawkeye, they try to predict the future based on the past experience. So they are trying to simulating the behavior of the optimal replacement policy here. So they have a prediction table. And based on this prediction table, they try to predict the future. But the possible attack here is the prediction table can be changed. But and we are currently working on it. I will not explain this idea in detail because one of my PhD student is working in this problem statement, and I think I should not explain it in more detail here. But you can also try that. If you read the Hawkeye paper, you'll try to understand that how the prediction table can be changed. Means how you can write a application such that you can change the prediction table and that it can degrade the performance and all. Okay, so these are some examples, possible attack example from replacement policies. If you want to know more about replacement policies, if you want to work more on these attacks, then first try to understand all the existing replacement policies, and then think about what are the attacks possible, or what are the new attacks that you can propose. Okay, so now I'll go for another concept called cache partitioning. I think I I've explained it in my last lecture, and also Dr. Vishwandan Panda has explained the concept of cache partitioning, both way partitioning and set partitioning. But I'll only concentrate here on way partitioning. So what is way partitioning? So I've already mentioned that if this is a cache, this is a set associative cache, then rows are called set and columns are called ways. So way partitioning means suppose there are two cores and both the core are running to different applications. Then now what happened? Maybe the application demand is different. Then maybe the application 2, which is running executing in core 2, needs more storage, more cache space as compared to the application that is running on core 1. So in that case, what we can do, we can partition the cache in such a way that the application 2 that is running on core 2 can access the more cache space as compared to C1. Okay. So the partition can be either static or dynamic. So here you can, this is the example of static partitioning here. So you can see I have partitioned the cache here. It means that the C1, the application that will run on C1 can use only 3 ways from all the sets, and the remaining ways are for the applications too. So you have to understand one point here is that though I have given a partition here, you don't think that only this left 3 will be assigned to C1. Here only count is important. Then out of 8, only 3 will be, maximum 3 can be used by C1, and the remaining should be used by C2. So that is called static partitioning. Okay. But there is a disadvantage of static partitioning. The disadvantage means if sometimes the application behavior changes, that after some time the application that is running on core 1 needs more space, and the application running in core 2 need less need lesser space, then you cannot change the partition, and at that time performance will degrade. Okay, so basically no one used static partitioning actually because of this disadvantage. So that's why the partitioning that normally used in last level cache is called dynamic partitioning. So dynamic partitioning means based on when your computer is running, based on the behavior of the applications, the partition should change. Maybe suppose based on the initial behavior, this was the partition initially assigned, but after some time based on the behaviors, assume that after some time the application 1 that is running on core 1 needs more space. So based on the behavior, maybe we can change the partition from here to here like this. So now the question is, based on which behavior will change the performance. So again, the concept of dynamic set sampling will be required here. So what normally happens, for each core a small data structure is used. It is called utility monitor. If you want to know more about it, you can read this paper that I have mentioned here. This is a very, very interesting paper proposed in 2006, but don't think that it is old. Even today people use the concept for different partitioning techniques. So this is a very important paper, or you can say very baseline paper for cache partitioning, very important baseline paper. So what they do, they use 2 utility monitors like this. Here, this is a small data structure, and what they do, they try to monitor one utility monitor for each core. So here there are 2 cores, there will be 2 utility monitors. So by this utility monitor, they try to monitor the performance of the cache, and then based on this they partition. But when they monitor, it's not possible to monitor all the set. So again, the concept of dynamic set sampling will be here, that they will only monitor the behavior of a fixed number of set. So normally it is 32 or 16 number of 16 set out of many sets. So only a fixed number of set, for fixed number of set, they'll observe the behavior. How they'll observe the behavior? Basically, in this structure, all the 8 ways will be assigned to core 1. Here also all the 8 ways of this set will be assigned to core 2, and then they will try to simulate that if the entire cache is given to C1, then what will be the performance? If the entire cache will be given to C2, what will be the performance? If 50% given to C1, 50% given to C2, all this combination they can check from this utility monitor values that they will collect. So, but the most important part here, these values, I am not explaining in detail because it's otherwise I have to spend a lot of time here. But the main important point is they are concentrating on a fixed number of set, and based on the behavior of this fixed number of set, they are partitioning all the sets. So again, this concept of DSS, dynamic set sampling, is using here. Okay. So now what is the possible target attack? A possible attack here is if the attacker knows somehow knows which are the set that are used as the DSS set for dynamic set sampling, then maybe attacker can incorrectly partition the cache. Maybe when the partition should not be like when the partition should be like this, the way it is, maybe the attacker can attack those DSS set and maybe forcefully change the partition from here to here, which is actually no, which may not be correct. That's why it's in targeting the DSS, an attacker can change the partition incorrectly. That may be an attack. I don't know if it is exist or not, and but yes, I have experimented it and it's possible. But you have also not proposed it yet. But yes, based on my some initial experiment, yes, it is possible that if we know the target set, we can change the partition. Attacker can change the partition, and if it is incorrect partition change, then obviously it will hamper the performance. So I hope this cache partitioning based attack, one more cache partitioning based attack I'll explain, but after a few slides. Okay. Then I'll introduce a very important attack called time-based attack. So I think time-based attack is already discussed in I think different session already. And one of the well-known time-based attack is side channel attack. Though side channel attack is also possible with other, not just with time, but for example, in yesterday's lecture, they explained how side channel attack is possible based on the power consumption and all. But yeah, side channel attack is also possible with time difference. So what is this time difference? So if you know the property of a cache memory, if there is a hit in the cache, then the hit time, or if there is a miss in the cache, then we have to go to main memory. Suppose I'm only talking about the last level cache here. So if there is a miss in the last level cache, we have to go to main memory and fetch the block. It's a off-chip communication, right? So it will be, the latency will be very high as compared to if there is a hit in the cache. So there is a huge difference between hit time and miss time in the last level cache. So that is called time-based attack. Time-based attack means more latency is one category, less latency is one category. But for today's discussion, to make it simple, we'll always assume that high latency means binary 1, low latency is binary 0. So it will easy. You can also think it the other way. But for today's presentation or today's talk, remember that binary 1 means high latency and binary 0 means low latency. Okay. So now I'll not discuss side channel attack here because I hope it is already clear. I'll discuss more about covert channel attack. What is called covert channel attack? And throughout this discussion, I'll mention it as a CCA, covert channel attack. So you have to remember this term called CCA. So first, let me discuss the threat model. What is threat model? Threat model means the model or the architecture on which we assume, we think that this attack is possible. So we have to design or have to assume first a model that on this model, the attack is possible. So let us discuss about the threat model. So in threat model, the processor has multiple cores and some of them are specially designed for executing secure application. For example, if this is a processor here, there are 2 cores, assume that C2 is designed for executing the secure applications. Or you can drop this part also that's specifically designed for secure application. You can also think like this, that there are 2 cores and in some core, maybe secure application can execute. Okay. The application running in a secure core cannot communicate with other application. Means if there is an application that is running on C2, and if it is a secure application, then that application cannot communicate with other application that is running on other core or the same core also. That is the threat model, means they cannot communicate. So if there is an application that is running A2 here and there is an application running A1 here, if I say that they cannot communicate with each other, it means that one point is they are not sharing any block. If they are not sharing any block, they are not communicating. And if they are sharing also, then A2 has no write permission, because if A2 can write something, then since the secret information is with A2, then if A2 can write in a shared block, then from that shared block, A1 can access it. So there are 2 things here. Either these applications are not sharing any block, and if they are sharing also, then A2 has no write permission. So these are the assumptions and these are the threat model I'm using. Now, what is the CCA attack, covert channel attack? For covert channel attack, as I'm saying, I'm always assuming that the application that is running in C2 is secure, and but assume that there is a Trojan application running here. Trojan I'm representing ST. Somehow a Trojan application is running in the secure zone, and that Trojan application knows a secret information. So now every information in a computer is a binary string, right? So assume that 100111000. Suppose this type of binary string is there, and that this is the secret information. But now the Trojan application that is running in core C2 knows that secret information, and it wants to communicate this this secret information with the spy application that is running in core 1. But as per the threat model, they cannot communicate directly. Means this Trojan cannot directly send this secret information to spy. Sometimes the spy is also called receiver. I'll not write receiver here, otherwise you'll confuse, because but normally sometimes sender is also called, spy is also called receiver, and Trojan is also called sender. But let us go with Trojan and spy only. So spy is expecting a secret information from Trojan, but how to send, because direct communication is not possible. That is called covert channel attack, that based on the or misusing the some properties of last level cache or any cache memory, they can establish a covert channel through which the information can be communicated. That is called covert channel attack. Okay, so I'll give you an example of covert channel attack in next slide. So to understand covert channel attack, first of all, we have to fix a eviction set. I'll explain it. For example, spy is running on C1. Always remember, spy is running on C1 and Trojan is running on C2. Trojan has the secret information. So assume that spy will go for some block access like this: A, B, C, D, E, F. All the capital letter blocks are named with all English capital letter, and Trojan blocks are named with all small capital letter: A, B, C, D, E, F. Assume that all these blocks are mapping to a particular set, that is set number 1. They are all mapping in this set. So what is these blocks? These blocks are decided by spy application and Trojan application already. Always remember, Trojan application means Trojan wants to send, means Trojan is also malicious application. So before starting the attack, spy and Trojan will decide their eviction set. Eviction set means set of blocks which are mapping to a same set here in last level cache. So now I'll explain prime probe attack. So in prime probe, first phase is prime. So in prime phase, what will happen? Spy will request. Remember, spy application is running on core 1. So spy will request for all the blocks that is in its eviction set. So ultimately, A, B, C, D, E, F, G, H, all blocks will be available in this last level cache after prime phase, because in prime phase, spy is requesting for all these blocks. Okay. So after this prime phase, there is a waiting period, and that time Trojan has to decide something. Suppose the bit message is 101. So first bit that Trojan want to send is 0. So every time Trojan will be two choice. Either it need to send binary 1 or binary 0. Suppose Trojan want to send binary 0. Then what it will do? Suppose, as I said, binary will always think like this. The binary 0 means no delay. So after prime phase, if Trojan want to send binary 0, Trojan will not do anything. Okay, Trojan will not do anything. Suppose cross means Trojan is not doing anything. And if Trojan want to send binary 1, then Trojan will do something, but I'm not going with binary 1. First, let us understand how Trojan will send binary 0. Prime phase, A, B, C, D, E, all these blocks are requested by spy, and after prime phase, this is the status of the cache memory. Okay, and now after prime phase, if Trojan want to send 0, it will not do anything. Then probe phase. In probe phase, spy will again request for the same blocks, that is A, B, C, D. The spy will again request for the same blocks. So if it's at this moment, if in the probe phase, if the spy will request for the same set of blocks, then all the blocks will be hit in the cache, isn't it? Because A, B, C, D are already in the cache. If the probe will in the probe phase, if spy will request for this block, all these blocks will be hit in the cache. So hit in the cache means less amount of time. Okay, now we'll see that how Trojan will send binary 1. In case of binary 1, after prime, what Trojan will do? Trojan will also request for some blocks, A, B, C, D, its own blocks. They are not sharing this block. These are completely separate blocks. Okay, so now, and what I said that both these blocks, either these blocks or they are mapping in the same set. So after the prime phase here in this stage, if Trojan requests for this block, then what will happen? According to the replacement policy, these blocks will be replaced with the blocks of Trojan, like A, B, C, D, E, F, G, H. They will be replaced with the blocks of Trojan, right? Now, when the probe phase here, when the spy will request for its own block A, B, C, D, those blocks will be missed in the cache. And miss in the cache means you have to go to main memory and have to fetch it. So more delay. So that's why I'm saying less delay will be considered as 0, and more delay will be considered as 1. So in this way, Trojan can send 1 bit of information. Then if they repeat this process multiple times, then based on this process, they can send any number of binary bits. So it means that they are able to send a secret information from Trojan to spy. So that is called covert channel attack. How this attack is happening? There is no direct communication is not allowed, but still based on some misusing the properties of cache memory, they are establishing the covert channel. So this is called covert channel attack. So here I have cited my own paper here, but don't think that this is this paper is a survey paper. Why I'm citing it here? Because if you read this paper, different types of side channel and side channel attacks or covert channel attacks is discussed here. That's why I have cited this paper here. Okay. So now this is the prime probe. Another way to handle covert channel attack is called, another way to perform covert channel attack is called flush reload. Flush reload is also very interesting, but there is an assumption here. In case of flush reload, what we will assume that spy and Trojan share some blocks. So in that case, the eviction set will be not different. There will be only one eviction set, suppose. This is the eviction set. So here spy and Trojan are sharing the block. As I said, this is also possible that both spy and Trojan can share the block, but Trojan has no write permission, because if Trojan had write permission, maybe Trojan can write the information to this shared block, right? But that's why I'm saying they are sharing the block, but Trojan has no write permission. Trojan spy can maybe write, but Trojan cannot write. Okay. So now in this case, flush reload, what they do initially in the flush phase, what they will do, they will always target a particular set. So if they are again targeting set number 1 in flush phase, they will flush the set like this. The set will become empty. Now, second phase is either sending 0 or 1. So as I said, 0 means more delay, I said, no? So what they will do, if Trojan want to send 0, then Trojan will request for these blocks, A, B, C, A, C, D, all these blocks. In this situation, if Trojan will request for this block A, B, C, D, what will happen? These blocks will be fetched from the main memory and stored here. A, B, C, D, E, F, G, H, right? So then after this phase, there is a reload phase. In reload phase, spy will request for the same block again. You have to understand this. In flush, we removed everything from the set. In this phase, when Trojan requested for this block. Trojan requested this block means these blocks are now available in the cache. Now in reload phase, spy is requesting for the same blocks. Now when spy will request these blocks, now at this moment, all blocks will be hit in the cache. So less time, because hit. So less time means 0. Now how Trojan can send 1? If Trojan wants to send 1, so after flush, this was the condition of cache after flush. So if Trojan want to send 1, it will not do anything. It will not do anything. So in case of reload, when spy will request for this A, B, C, D, everything will be a miss in the cache. So you have to go to main memory, fetch the blocks of high. So again, more time means higher time, higher delay means binary 1, lesser delay means binary 0. So using flush reload also, a covert channel attack can be established. So all these things are already in literature. So these covert channel attack is already exist in literature, and there are countermeasures also possible. Let me. That's why I have written here CCA countermeasure. There are different countermeasures that exist. You can read my survey paper here. Different kind of detection and defense mechanism is there. Detection means what? First, we will try to detect that if there is any covert channel attack is going on or not. If we can successfully detect it, then we can mitigate the attack. So mitigating the attack, the best, the straightforward solution is suspend one of this application, right? Suspend the spy process. If we suspend or terminate the spy process, then there will be no further covert covert channel attack. But the problem here is we cannot suspend every time. Because why? Because the detection mechanism may not be 100% accurate, right? And if the detection mechanism is not 100% accurate, then you may end up terminating an innocent application also. So the solution that people are thinking is we should allow to continue them, but even if they are executing, they should not perform any covert channel after detection. So those mitigation techniques are important. So there are some you can see there are some detection techniques here explain. There are other detection techniques also. I have only mentioned 2 here. So you can also understand how a detection technique can be designed. So most of the time what they are doing, they are targeting a set and they are removing each other's blocks. So there are a lot of conflict misses arising, right? Because they're conflicting with each other, then removing the blocks. So if you can somehow detect those conflict misses properly, and then based on these conflict misses, I think you can detect that whether there is a covert channel attack is going on or not. So detection is this. There are other detection techniques also. I'm not explaining, just giving you a hint. And now how to defense? There are different defense mechanism is there. One possible way to defense is prefetching. So I hope I have explained the concept of prefetching. So if you see, there are 2 papers here, defense, both are depend on prefetching. They are prefetching. Prefetching means if we, for example, if we go for flush reload attack, then flush reload attack, first in flush, we are flushing the set, and then in case of suppose the Trojan wants to send 1. So in that case, what I said, Trojan is not doing anything, right? Trojan is not doing anything. Why? Because in case of reload, spy should face a miss in the cache. But in this phase, if the attack is detected, then what you can do, you can prefetch some of the block which the spy will request in reload phase. If we prefetch some of the block and already place like B, D, and F is already there, if you can prefetch, then at least this miss time will reduce, because B, D, and F will be hit during the reload phase. So this is just an example. There are also challenges with using prefetching also here, but I'm not going in more detail. As I said, I'll just give some ideas that what are the possible direction of research, what are the research direction possible. So if you understand the basic cache architecture, then there are 2 possibilities. One, you can either propose new covert channel attack, or you can also work on the defense or detection mechanism. Why I'm saying you can work? Because most of the defense and detection mechanism has high performance overhead. The same thing that I have mentioned in when I was discussing about row hammer attack, the same thing is true here also, that the existing defense mechanism have hard performance overhead. Means to to detect and prevent this type of covert channel attack, some mechanism we have to implement which will degrade the performance of innocent application. So to proposing some that's why I've written research possibilities here. Hardware efficient detection and defense mechanism. This is one possible research is possible in this direction. And another research possibility is new attack on the existing countermeasures. There may be some counter like 1, 2, 3, 4. These we can consider these 4 papers as countermeasures. What about if you can propose a new attack on this existing countermeasure, assuming that these countermeasures are implemented in the cache, but on top of that, how you can propose a new attack. So this area is always open, and you can also think about it. Okay. So I think it is 11:02. So I am stopping here, and I'll wait for your. If you have any question, I'll try to answer them, and then I'll continue after. I think from 11:10. 11:10. Yeah, 11:15. I think. Now, Dr. Kalyan, we started at 11:10. I think, right? At 10:10.
Sure, up to you.
Okay, so I'm stopping now, and I'm waiting for questions and doubt clearing for 5 minutes.
Okay.
And then again, I'll start at 11:10.
Okay. Yeah. 11:10 or 11:15?
Oh, sorry, 11:15.
Okay. So there seems to be a question in the chat box.
What if spy and Trojan are accessing different set? See, spy and Trojan both are malicious application, right? So they must have some pre-decided rules that okay, we'll do this thing. That's why we'll then only we'll attack. We can able to attack. So if they are accessing different set means they have no communication. So definitely there will be no attack possible. But yes, after this break, I will explain some covert channel attack, which is not, I think they are not proposed yet, where though the spy and trojans are accessing different set, covert channel attack is possible, but those covert channel attacks are different. So I'll explain it. But whatever the concept of covert channel that I've explained, for this concept, both trojan and spies should target the same set. Okay, so let us start the second part. So now I'll start with the covert channel attack on cache partitioning. So previously I explained all the covert channel attack here on assuming a LRU replacement policy, right? So yes, here one more possible research direction is what about the other replacement policy? Because all the covert channel that I've explained, that it will fetch the block and then Trojan will try to either remove all the block or not remove any block of spy, that is spice block from the cache memory. So in that case, somehow we are assuming that the replacement policy is LRU. What about if it is a DIP, right? So in that case, all the blocks may not be evicted from the cache. So it's still open that if suppose there is a very recent replacement policy is going on in the cache, then this already existing covert channel attack based on prime probe or flash reload, is it possible or not? Flash reload, I think possible, but prime probe is possible or not? It's still we can check. So these are also, I think, you can explore. And now let us discuss a covert channel based on cache partitioning. So this is proposed by it is from my lab. So this, based on this attack, again the covert channel means I am assuming that Trojan is running here and Trojan has a secret information like this binary bits, and now this information Trojan wants to communicate with the spy. So now here we can assume this attack is not based on a particular set. This attack again is based on the partition change, because we are assuming that this attack is possible if there is a dynamic partition is there, means the cache has a dynamic partitioning technique. So I have already explained you what is called dynamic partitioning and how dynamic partitioning can change. While I was explaining dynamic partitioning, I mentioned that if some attacker knows that which are the DSS set, like dynamic set sampling, so which are the DSS set, then based on this it can change the partition. So here also we are assuming this, that the attacker knows which are the set called DSS set, and based on that it can change partition. So assume that initially in the prime phase first attacker will change the partition. Attacker means spy will change the partition, and a partition is now here. Suppose partition is there, means all this left side are now for spy. And after this, what spy will do? Spy will probe the data, and here spy can use multiple set also. Assume that spy will probe its data here, spy will probe its data here. I'm not using ABC because I'm using multiple set to save time. I'm saying that assume that these are the spies data now, because partition is now here. So this all this thing will be happening in prime phase. Now the second phase is before probe phase. Now Trojan has to decide whether it should send 0 or 1, right? 0 or 1, what it need to send. But for both case, either it need to send 0 and 1. See what first Trojan will do. Trojan will change the partition again, because if Trojan will again attack those DSS set, and based on this DSS set, Trojan can change the partition as per his requirement. So assume that Trojan change the partition from here to here again. Now this is the partition change. But one thing you have to understand here is that when a partition changes, means suppose partition was initially here, and now partition changes from this position to this position. In that case, when the partition changes, the block C, in this area, now the blocks are of spies are still there. So what normally do when we change the partition, we do not evict the block from this side. We slowly evict them. Whenever there will be a new request from target will be there, at that time we'll slowly change the partition. Not like only it is that okay, partition will be now here, but data is still there. This is the policy of cache partition to reduce the performance overhead. Okay, so now Trojan will change the partition again from this position to this position. Now in this case, if Trojan wants to send 0 or 1, so here there are 3 sets. So Trojan can send 3 bits at a time, not just 1 bit. Okay, so assume that if Trojan suppose Trojan want to send 0 to a particular set, the Trojan will what Trojan will do? Trojan will not do anything. Suppose through a particular set, Trojan want to send 1. So suppose Trojan want to send here 0, here 1, here again 0. So Trojan what will do? For 0, Trojan will not do anything. For 1, what Trojan will do? Trojan will request for his own data for this set, and it will remove this. It will remove all these blocks. Maybe only one block is there. All the remaining blocks from this side will be removed because Trojan will request for his own data, and now here Trojan's data are there. So let me write T, 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 T. These are Trojan's block. So now Trojan's blocks are here. So this phase is done. So now again in probe phase, what the spy will do? Spy will again request for the block that it has requested in the prime phase, right? So in prime phase, so what will happen when probe phase, spy will again request for the block. Here less time because everything will be hit. Here less time, everything will be hit. So these two bits will be considered as 0. Here Trojan spy will take more time because most of the blocks are missed because now these blocks are filled with Trojan's blocks. So in this way, in this CPCC attack, the Trojan can send multiple bit at a time. Why multiple bit at a time? Because this attack is a little bit slow. Why? Because for one round of attack, we need to change partition 2 times. So in this way, the attack is little bit slow. But since we can target multiple sets, so that's why it is a covert channel attack is still possible here. So this is proposed by us. And what are the other possible attacks? We are exploring other possible attacks also. For example, initially we did it only for 2 cores. So now we are trying to explore, means thinking that we're trying to explore it, that if there are multiple cores are there, then what are the possibility of CPCC attack, and also we are still exploring it. So I will not disclose it here now. And countermeasures, yes, the efficient countermeasure is yet to be proposed. We have not proposed any efficient countermeasure. Honestly, we didn't find any efficient countermeasure. One possible countermeasure is when we are changing the partition, evict all the block. For example, when I said that initially partition was here, when I move the partition from this position to this position, remove all these blocks. Remove all these blocks of spy. So if we maintain this, normally that is not followed in a dynamic partition. If we maintain this, then I think that can prevent this type of attack, but that will degrade the performance again. As I said, that proposing a performance efficient detection or defense mechanism is a challenge. So this efficient countermeasure is yet to be proposed. So you can also think about it. So this is one attack, covert channel attack based on cache partitioning. So I think you are understanding that to work on this cache security or this cache based attacks, what is important is the knowledge of different microarchitecture, the different techniques like replacement policy, cache partitioning, prefetching. The more you know about these techniques, then the more confident you will be to work in this area. Otherwise, if your knowledge is limited in these areas, then you cannot think about new attacks, you cannot think about new partitioning. So you need to spend at least some time, at least 3-4 months of time on understanding the basics of computer architecture or memory if you are completely new in this area. And if you are already working in this area, then it is fine. Okay. CCA based attack on cache coherence. This is another attack that this attack is already proposed. It is proposed in 2018. So the paper is mentioned here. So last session, I have quickly explained the concept of cache coherence, right? So this attack is based, it is misusing the advantage, misusing the, what you can say, the properties of cache coherence. So how this attack is possible, I'm quickly explaining it. Suppose in prime phase, again, Trojan is here, spy is here. Spy will request for a block. Suppose A and B. Spy is requested for 2 blocks, A and B. I have written in 2 different sets. So assume A1 and B1, suppose. So assume that A1 and B1 are now mapping to 2 different sets. They are not from same set. That's why I say not easy to detect. That part I'll explain later. But here now assume that in prime phase, spy has requested for 2 blocks, A1 and B1. One is mapping in this set, another is mapping in this set. Now, okay. Now Trojan either want to send 0 or 1. If Trojan want to send 0, Trojan will not do anything. Okay. But if Trojan want to send 1, then Trojan will also request for these 2 blocks, A1 and B1. In that case, what will happen? If okay, one thing I have missed here, that in prime phase, the spy will request these 2 blocks in shared mode. Shared mode. So in prime phase, this spy has requested this A1 and B1 in shared mode. Now Now this is Trojan. So if Trojan wants to send 0, Trojan will not do anything. If Trojan want to send 1, Trojan will also request for this to block. If Trojan requests for this to block, what will happen? There will be a hit for A1 and B1 both in this case, last level case. So what will happen? Now this A1 and B1 are also available in T1 in Trojan also, because Trojan is also want to access them in shared mode. So now in A1 is available in both 1 and 2, and B1 is also available in both 1 and 2. Now, okay, so this phase done. Now probe phase. In probe phase, spy will request for this block in write mode. Means in probe phase, spy will say that, okay, I want to write something in this block. So though the blocks are already, both A1 and B1 is already in its L1, but they are also in here also. So if now spy want to write something in A1 and B1, it cannot directly write, because according to coherence protocol, it don't have that, it has not write permission, right? So first of all, what a spy need to do, spy will send a upgrade request here, that I want upgrade request to this this lower level. And now in this case, now check if it is 0 and 1. In case of 0, in case of 1, what will happen? When a spy will request for a upgrade request here, that I want to write, give me write permission for A1 and B1. So when the request will reach here, here the directory will check that, okay, this A1 is now currently shared with both A1 and A2. So I cannot directly give write permission to spy, because if I currently give write permission to spy, then there will be 2 copies of same thing, right? This Trojan will have 1 copy and spy will have another copy. So what this coherence protocol will do, it will send an invalidation message to this Trojan that, okay, look, you have a copy of A1, so invalidate because another person want to write something on it. So Trojan will invalidate its copy, and then it will send an acknowledgement here. And after getting this acknowledgement, then the write permission will be given to here. Okay. So these things, sending invalidation request here and getting acknowledgement, will take some time. And this is the extra time for bit 1. In case of 0, what is happening? In case of 0, Trojan is not doing anything. So in that case, the blocks are not, A1 and B1 are not shared among both the cores. So in that case, in probe phase, when this spy will request for write permission, this write permission will be immediately granted. So in that case, this delay will not be required. So based on this delay, means in case of 1, it will be shared such that the invalidation is required. So that invalidation will add extra time. So based on this, the covert channel attack can send either 0 and 1. So in that case, why I have written here not easy to detect, here you can see that it is not mandatory that all the blocks need to be from same set, because there is no conflicting. They are not removing each other's block. So all the detection mechanism which is based on conflict misses, or which is based on who is removing each other block, which are based on targeting a particular set, those detection mechanism will not work here. It may be possible that another detection mechanism can be implemented for it, or maybe already implemented, but at least the detection mechanism which are used for a targeted set or for the conflict based attack, those will not work here. That's why it is not easy to detect everything. But this idea, I think this attack is already proposed. You can also think about the countermeasure. I'm not sure about, maybe you read this paper once. I'm not sure whether they have proposed any countermeasure or not, but you read this paper. It's a very interesting paper. Okay. Now other possible attack, I have not explored it yet. Honestly, this part we are not exploring at this moment. The possible countermeasure also I am not. That's why I am not very aware that whether they have proposed it or not. But yes, I think definitely you can work on it. As I said, this is not easy to detect. Okay. So cache coherence done. Cache coherence based attack is done. Now I'll start a new thing. I mean, I'll stop the CCA based attack here for some time. I'll again discuss CCA based attack after at the end, I think in the last slide. Now I'll stop the concept of CCA, and now I'll discuss about the multi-bank cache. So for next 2-3 slides, I'll not discuss about any attack. I think I'll only discuss about multi-bank cache. Why multi-bank cache? Here you can see the last level cache that I'm discussing here. I'm assuming that there is only one last level cache, which is not true, because if there is only one last level cache in modern days, there are multiple cores exist in the processor, right? So if all, so there will be a so in that case, all the core will try to request for try to access the block, the same L2 cache. And this is also one problem. Another problem is it is a non-uniform cache. So all this thing I'll discuss in next slide. So here normally what happens, this type of cache nowadays is divided into multiple banks like this. Now each bank is a set associative cache. So you can relate this to figure. What is the difference? Instead of one bank here, the one large size cache, here there are multiple small size cache. Each is called a bank. Now each bank is a set associative cache, and now they are connected with network on chip. I hope you understand now what is called network on chip after the session of Dr. John Josh. So I'm not going in more detail about network on chip. So they are connected with a NOC, right? And there are multiple banks here. So now based on now this policy can be either static or dynamic. Oh, sorry, it is called NUCA. First of all, it is called NUCA, non-uniform cache access. Why it is called non-uniform cache access? Because suppose this code C2 wants to access this bank, then this bank is very near to him. If there is a connection like this, then this is just one hop distance. But now if this C2 want to access this bank, then C2 the request from C2 has to travel through this line, and then it will reach here, right? So multiple hop is there. So that's why cache access is not uniform here. This is non-uniform cache access is possible. That's why it's called NUCA. But there are two types of NUCA design here: static NUCA and dynamic NUCA. So now let us first discuss about static NUCA. So in static NUCA, suppose this was your last level cache. Now it is divided into multiple banks. Now banks are connected with network on chip. Okay, these are the NOC routers. This you can say NOC router, and these are NOC interconnects. Okay, and you have to also assume that these all are set associative cache that I have not mentioned here. So now in case of set associative cache, we know that first of all we have to map a particular set. We have to fix a particular set based on the set index, then and then a block always mapped to a particular set. But here there are multiple banks also. They're not just multiple set. First of all, we have to decide if there is a block. Suppose this is the block address. This is the block address given. Based on this block address, first of all we have to decide in which bank it will go, isn't it? And then once the bank is decided, then you have to check then in which set it will go. So that's why the index bit is now divided into two parts: bank index and set index. First of all, based on bank index, we will go to a particular bank, and then based on set index, inside this bank will go to a particular set. So now the index part is divided into bank index and set index. The remaining thing is same. Now why we're saying it's static NUCA? Because here static NUCA means we are always mapping a particular block to a fixed location. Means based on the bank index, a block is always going to a particular bank. We cannot place the block in some other bank, because based on the index, it is always mapping to the fixed bank. That's why it is called static NUCA. Now, there are advantages always there in static NUCA, because it is easy to search. Because if based on the if the address is given, from the address only we can we know that which bank we need to go and where to search. But there is a disadvantage also. Disadvantage of SNUCA is, suppose this is the core. Okay, this is the core, and this core is requesting for a block, which block is residing here in this bank, and this core is requesting this bank multiple times. So every time the request has to travel all this NOC interconnect, and then it will reach here every time, because it is static NUCA. There is no option or no benefit or no support that this block can be migrated from this position to a nearby bank of this core. If we can migrate this way, then this length will be reduced, but that is not possible in static NUCA. That the migration is not possible. Block is fixed. So that is the that is called static NUCA. Advantage is always there, that it's easy to search, and disadvantage is migration is not there. So to support migration, there is another NUCA is proposed called DNUCA. So DNUCA means dynamic NUCA. In dynamic NUCA, the banks are normally divided in like this into multiple bank set. These are called bank set. So bank set can be in other way also, but here I'm assuming that each column is a bank set. So in each bank set there are 4 banks. So now in dynamic NUCA, the property is a block can be mapped to a particular bank set. Suppose a block is called B, it is mapping to this bank set number 1. So it means that it can place any of these 4 banks inside this bank set. The B can be placed here also, you can place it here also, you can place it here also, and it can place any of these 4 banks. This is called, that's why it is called dynamic NUCA. So it means that if suppose there is a bank here, block here, and this core is requesting this block multiple times, then this block is allowed to migrate from here to here. We can migrate it from here to here. If we migrate it, then after migration, the communication latency will be reduced, right? So this is allowed in DNUCA. But now what is the challenge in DNUCA? The challenge here is now a block has different possible banks. Means if we want to search B, you have to search all the 4 banks in bank set 1, right? So DNUCA only performs better if there is a efficient searching mechanism. So this is another huge area of research, that how to reduce the searching time of DNUCA. So I'm not going on all of this. So there are some research paper that I am citing here. So they either proposed a DNUCA based technique, and they also they discuss about how to reduce the searching time of DNUCA and all. So this is a example where I have discussed about how migration is happening in DNUCA. So migration means, suppose this is a block which is heavily requesting by this core, then we can move this block from here to here. Okay, this type of migration is possible in DNUCA. Now, a possible covert channel attack on DNUCA. So a possible covert channel attack is, for this, assume that there are 2 cores, C1 is here and C2 is here. And now assume that a block accessing by C1, suppose that a block is shared by both the core. So initially the block is here and C2 is accessing it. Okay. Now suppose Trojan is here. Now suppose Trojan can do something such that it can force this block to migrate from here to this position. And now if it can successfully migrate this block, then the latency of this block for in terms of C1 will change. Now C1 has to travel all this and it will change. So what I'm trying to say here is that if the block is here, then because it is a non-uniform cache access, and access latency will be less for C1. But somehow if the block is moved from this position to this position, then access latency will increase. So in this way, high access latency and low access latency can be categorized. So binary 0 and binary 1 can be transferred. So I'll not disclose it in more, because we are working on this problem statement. So maybe if from this point you can also propose something, then it is good. But I cannot disclose it in more detail. But yes, we are working on CCA based attack in dynamic NUCA. Okay. So now I'll discuss about multi-processor. So suppose this is a processor where there are multiple cores. There are 6 cores here. All the core has their private L1 cache, and all the code sharing a common large size L2 cache. Now we can see the large size L2 cache is divided into multiple banks. These small concept are bank, and assume that all these banks are set-associative cache and they are connected with an NOC. Okay, so this is one design. This is called CMPU centralized LLC. LLC means last level cache. Why centralized? Because you can see the last level cache is placed in the centralized location. Now I'll show you another design of multiprocessor. It's called TCMP. In TCMP, there are multiple tiles. First of all, you understand the structure of a particular tile. Each tile have a core, and then L1 cache, L1 I cache, and L1 D cache, and this L2 and the L2 cache. And now there will be multiple tiles like this, and all the tiles are connected with some on-chip NOC. So this is called TCMP. Okay. So now here, one important point you have to understand it. If you see this left side diagram here in this CMPU centralized LLC, here the cache is shared. Cache is shared means if a block is available in this bank, then this block will not be available in any other position. Assume it's a static NUCA, suppose. So it means that the cache here is shared but divided into multiple banks. The same concept is true here also. Here the LLC, that is L2 cache, each shared but divided into multiple parts, and each part is assigned with a particular tile. So why this is important? Because now I'll explain TCMP from here. Suppose this tile T4 is requesting for a block. So now this is the core of T4. First it will request to its own L1. If there is a miss in L1, then it will request for the L2. Which L2? There are multiple L2. One L2 is local here also, right? This is the local L2. So do you think that every time if there is a miss in L1, it will request to the local L2? No. If you remember, if it is a static mapping also, if it is static NUCA also, then accessing a L2 bank depends on the bank index, right? So if assume it is a static NUCA design, if there is a miss in this L1, then to request for a L2, first of all, you have to find out the bank index. Suppose the bank index is 1111, then what will happen? If there is a miss in this L1, then to access the L2, we have to go to this tile, because the bank is in the block is in the L2 of this tile. So that is called home bank of that block. Okay, so that's why the concept that that I think this concept was also explaining by Dr. John in his presentation, that in tile-based architecture TCMP, when a core is requesting for a block, if there is a miss in L1, then when we need to fetch the block from L2, it is not necessary that every time we'll fetch from local tile. We have to request to the home bank, and home bank may be in a remote tile. So that's why there will be the cache miss request has to travel through the NOC, because this request will travel through this line and it will reach in this tile. So the cache miss request has to travel through the NOC and it will reach to the home tile, and from the home tile the block will be again sent back to this tile. So this is the procedure. That's why here, if there is a hardware Trojan here sitting here, and this hardware Trojan can divert this request from this position to this direction to this direction, then there will be a problem. So I'll explain all these things here. Don't need to understand hardware Trojan, but if you are understanding TCMP and how a cache miss request can and may need to travel through NOC, if you are understanding this concept here, then this is enough. Okay. So I think now I'll go start with NOC based attack, network on chip based attack. So I'll not explain the details of NOC, because I'm assuming that you already know it after the lecture of Dr. John Josh. So here you can assume that this is a NOC. Initially you can assume all these as a router, means these are routers, and they're communicating from one router to another router. So I think the concept of hardware Trojan is also explained in his lecture. So what I'm assuming here is that the router has a hardware Trojan. Some router, not all. See, here you can see the red, a router color with red has some hardware Trojan, malicious circuit is there. So that all the router which is hardware Trojan, I'm saying them as HT router, hardware Trojan router. Okay. So now, what are the different attacks possible if there is a hardware Trojan router available? Hardware Trojan router means this router has some malicious circuit and it can do some malicious activities, which should not be allowed. And why the hardware Trojan is possible in NOC? Because these different the modules, when we design a chip, we collect modules from different third-party organization and then we combine it. So there are, I think, there are different speakers already discussed about this. There are why there is a IP issues, why we collect IPs from different vendors and then we combine it. So it may be possible that some routers have some malicious circuit. So now what are the possible what are the attacks possible? Some of these attacks are already proposed and some are just my imagination, but I think you can discuss more, you can do more research on it. First, I will concentrate on a particular threat model 1. In threat model 1, I'm assuming that the HT router can modify a fleet and the NOC has no retransmission and error correction. So first of all, I have to explain you what is called fleet. So suppose if there is a network interface here, NI connected with this NI wants to send a packet. This is the packet P to this NI. This is called network interface. Okay. So this packet, before injecting this packet to NOC, because this packet has to travel through this line, right? So this, before injecting this packet to this NOC, this packet will be divided into multiple fleets, like small fleets. Okay, like this. And there will be a head fleet. First fleet will be head. Suppose this is the head fleet. And last fleet is the tail fleet. I think all these things are also explained by Dr. John. So now, this NI will divide this packet into multiple fleets, and first the head fleet will send through this NOC. And head fleet has this head fleet has a source node ID, destination node ID, and some other information also stored in head fleet. So based on this, because this routing is XY routing means first it will go to X direction and then Y direction. Based on this destination, it will go in this direction and then it will go to this direction to reach here in the destination router. Assume that this is the destination. Okay. So now again I'm discussing about the threat model. I'm saying that suppose this is a HT router. So if any fleet is passing through this router, then this router has capability to modify some bits of this fleet, of any fleet, maybe it's head fleet or body fleet or anything. It has capability to modify something. This is the first point. The second point is, I think Dr. John has already explained that retransmission is very expensive. So there is no retransmission, means if this NI is sending a packet to this destination, if destination has not received it, there is no retransmission. We are assuming that it will receive. So there is no acknowledgement kind of concept here. Okay, and also there is no error correction. Error correction means if the bit is received correct way or not, the error correcting code is not implemented. Basically, in a modern NOC chip, these concepts are not there yet, but in literature it is exist, that error correcting code, then I think retransmission and all these concepts are implemented in literature. But if we discuss about the real implementation of NOC, in real NOC, these things are not yet there. So that's why we are assuming threat model here like this, that HT can change fleet and there is no retransmission, no error correction. So in this case, all these errors are possible. I think all these errors are possible. First error, I think Dr. John has also discussed about it, converts the head fleet to a body fleet. So suppose this NI is requesting for sending a packet to this NI, okay, and now the packet is now divided into multiple fleet, and now head fleet is now fast moving, not this NI, not this NI, this NI, suppose. Okay, so head fleet will first move through this, but when it will pass through this HT, this head fleet will be converted to a body fleet. This is just one flag bit, right? So if this HT can do this type of changes, then what will happen? Then there will be a congestion, because now if this head fleet become a body fleet, then this may create a congestion. I am not going in detail, because if I want to go in more detail, I cannot complete it on time, because I have to explain other concept like virtual channel and all. So what I'm advising you that you can read this book. You can read this book. This book is in this book they have explained different attacks, and also they have explained the basic NOC architecture initially. And so you have to understand the basic NOC architecture. If I explain here all the basic concept of NOC architecture, then it will take some time, but I'm trying to explain all the attack possibilities upper level, so that at least you will have an idea, and then you can go deep into it. Okay, so now if this Transan can change the head fleet to body fleet, then again it can create congestion, because now when the body fleet will be moved from here to here, so that body fleet has no other it is not dependent on any head fleet, right? So this router is now clueless what to do with it. So so there is no mechanism currently implemented in this router how to handle this situation. So there will be a deadlock situation. So obviously, if there is a deadlock situation, then it will degrade the performance of the NOC. So you can see it's a performance-based attack. The same kind of attack is also possible, like if a body fleet is converted to a tail fleet. So suppose there is a big packet, and packet is divided into multiple fleet, and this is your head fleet, this is your tail fleet. But somehow, if this fleet is converted to tail fleet, then maybe a wrong message will send to the receiver, right? Convert a tail fleet to body fleet. If a tail fleet become converted to a body fleet again, then I think resources will not be released. So again, there will be congestion in the network. Okay, and now these are very important. This needs to, here I'm saying that changes the bits of a body fleet. Now, since HT has a permission to change some bit in a fleet, and there is no error correcting code is there, so it can change any information, right? So suppose there is a very important transaction going on, and then also, and if there is a very important value is sending, then in that value, if only 1 or 2 bits change, then there will be a major problem, right? Dr. Biman, I'll reply your question. Just let me finish this slide. Okay. So this type of so how to handle this type of attacks? I'm only explaining some possibilities of attack here on NOC. Okay, and now if this HT can change some bit of header fleet, that I think Dr. John has also explained, that some there is a block is moving from here and destination is this, it should go here. But what about the in head fleet? If this HT can change the destination from this node to this node, then now it will start moving in this direction. And what will happen for this? If you remember my example of this NOC TCMP, Then suppose, let me explain in terms of TCMP. In TCMP, there is a core here. A core is requesting for a block. Okay. Core is requesting for a block first in his local L1. It is missed in local L1. So it has to request to the L2, but home L2 is here. Home L2 is here. So the block has to travel through this line and it has to reach here. But what this HT did, it has forwarded this block instead of this line to here. It has changed the destination bit. So what will happen when the request will reach in this L2 bank, then it will find that, okay, the bank block is not mapping here. So it will simply drop. It simply drop. That means that this C1, this is still, the MSHR here is still waiting for the block and it will not receive. So in that case, maybe after some time, it again has to send a request. So that will increase the congestion in the network. So it is also a performance-based attack. So it can there are different types of attack also possible. What about changing the encoding bit? What is called encoding bit here? Encoding bit here means NOC compression. NOC compression means, suppose what I have explained here is that if there is a NI here and this NI want to send a packet, suppose this packet is of this length, okay, to this destination. This is the NI in this destination. So suppose this packet is now dividing into 16 fleets. Then all the 16 fleet has to travel through this link, right? So now what NOC compression works did, there are different works in this direction also. It is again in another research area, NOC compression. So they will try to compress this packet. Before sending this, they will try to compress this packet. And suppose after compressing, there is only 4 fleets. There are only 4 fleets. So instead of sending 16 fleet, they will only send 4 fleets. But for this, if we compress something, there with compression, they need some encoding bit to uncompress the data. So that encoding bits normally sent with the header fleet. So header fleet carries the encoding bit such that these 4 fleet in the destination can be again uncompressed to 16 fleets, right? Or the actual packet. So if assume that if hardware Trojan is sitting in this router, changes this encoding bit. If it changes the encoding bit, then every data will be corrupted again. So I think incorrect data attacks is also possible. So not all these attacks are already in literature, and honestly, I am also not experimenting it. But I think these are possible attacks, and you can try to experiment it or try to do further research in this area. Now I'll go about the second threat model where we are currently working. In second threat model, what we are assuming is that the HT router, this router cannot change any fleet, and the network has error correcting code, network has retransmission facility. Why I am assuming this? Because this is practical, right? But as I think, as we know from our previous lecture here, that retransmission is very, very expensive. But somehow I am ignoring the expensive part, assuming that it is there. Why I'm saying this? Because in literature, there are some works where, though it is not in real chip, but in literature, retransmission in NOC is there. In literature, error correcting code is already implemented. So I'm assuming some design from literature, not from the actual NOC design. And assuming that hardware Trojan cannot modify. Why? Because if you go to previous slide, you understand that if hardware Trojan has the permission to modify a fleet, then it can do anything. So assume that this type of hardware Trojan who has capability to modify must be detected in the fabrication phase. If it is not detected in fabrication phase, then it can do any type of attack. So it's very difficult to handle. And if it is not possible to detect with 100% accuracy in fabrication phase, then the research is open. You can propose any attack, any defense. There a lot of work still possible in this area. But still, what I will say that if this is the case, then the research in fabrication testing must be improved such that these type of attack where the HT can modify, then this type of HT must be detected. Otherwise, it will be very big problematic thing. Now here in this threat model, it's not like this. Here we are assuming that the hardware Trojan cannot modify any block. And also error correcting code is there, retransmission is there. So most of the that is required in NOC is there, but still it can problem. And what problem? One problem is called wrong routing. Wrong routing means, suppose there is a block from here, there is a N location, and this NI need to send a block from this location here in this NI. block will be the header feed flag, the block will be moved to this direction, and it should go this. But what this hardware Trojan will do, it will reroute in a different direction. Instead of sending it to this direction, it will send it to this. It will not change anything, but it will send to here. So after here, this router will find that okay, destination is this, so it will send to this. So what it is doing here, instead of sending it directly, it can send it to some other direction, so that other router has to send it. So in that case, the communication latency will increase. Sometimes it may also ping pong. So when ping pong situation arises, suppose this NI want to request to this NI. Now, so according to this, first the block should reach here and then it should go this direction. But instead of this, if HT move this block in this direction, then this router will again find that okay, the destination is NI. So according to XY routing, I don't need to move in X direction. I need to move in only in Y direction. So again, it will send here. So it may be a ping ponging effect. So you can understand that these type of hardware Trojan will not do anything, not changing or modifying any fleet, but still it is creating some problem. And it is maybe it's not a correctness attack. Incorrect means data attack, but it is a performance attack, because or you can say it's a DOS attack. So it will reduce the performance of NOC. So this attack, wrong routing, it is one of these attack is proposed here in this book. So these are I'm not mentioning all the authors of all the chapters separately, but if you read this book, you'll find wrong routing this concept is mentioned in one of the chapter. Okay, but they have given a countermeasure also for this. What countermeasure is, suppose in this case, because XY routing is there and a block need to be forwarded from this NI to this NI, and now this HT routed it in this direction. So now if this router is innocent, it can easily find out, okay, this block need to be sent from S2. Suppose this is S2 to S1. So it should not come to my end, because according to XY routing, it should go to upward direction. It should not come to my place. So in this way, this router can find out that okay, the previous router is a hardware Trojan. So what this router will do, it will send this information that okay, this router is hardware to all these nearby routers, and then there will be a shield will be created here, such that next time they will try to ignore this path. And if now S2 will want to communicate, then this communication will be done through this line, means from here to here. It will not go through this. So they will create a shield around this HT. So this is the countermeasure proposed in this book. But now other attack possible here. First point here, what about other routing techniques? So this is the XY routing. So this router can understand that okay, it is routing in wrong direction. Whatever if it is adaptive routing may change dynamically based on congestion and all. So this is still an open area. And also, if we assume that this type of detection mechanism is already there in NOC, means detection mechanism means the detection mechanism that can create a shield. So if we assume that this type of detection mechanism is already there in NOC, then also is it not possible to propose another attack on top of it? And also we are currently working on this, that assuming that this type of countermeasure is already implemented on NOC, is it possible to propose some more attack which can misuse these detection techniques? So one of my student is working on this area, so I'll not disclose the actual problem statement here, but you can also think on it. It's like this. You can relate like this, that initially there was possibility of hardware Trojan, so we have proposed a detection mechanism, right? So it's like you can relate it with a lot of the movie called Lord of Ring, right? There were 9 rings created, assuming to protect this world. So you can say we have also created this type of detection mechanism. Maybe you can relate this with 9 rings. Those are the detection mechanisms. But there is one more ring created, right? That is called Lord of Rings, to handle those rings. So it may be also possible that on top of this detection mechanism, there will be one more attack may be created who can misuse this detection mechanism and still perform do some performance attack or some data correction incorrectness attack. So the area is open, and you can also work on it. I think this is the last slide. So here NOC based attack for TCMP I will explain. I hope you remember the concept of TCMP that I explained. This is a simple NOC here. This is a simple NOC. Why simple NOC? Because this NOC may be required for other design also. For example, if you remember my centralized design, in centralized design, the last level cache was centrally present, but still the last level cache was divided into multiple banks, right? And those banks were also connected with NOC. So the NOC can be used for other purpose also, but in case of TCMP, there are some more attack possible. So if we want to convert this NOC design to TCMP, let me assume that this is a tile P L1 and there is a L2 here and there is a NI here, and this is connected with this router. So assume that every router is connected with a tile like this. Every core, every router is connected with a tile where each tile is a core, a L1 cache, and a L2 slice is there, and there is a network interface through which they communicate with other tile. Okay. So now in that case, the problem is, the first problem is, we cannot isolate a HT router. The solution that I have given in the previous slide, that if a HT is directed, you can create a shield around this HT and you can make this HT isolate. In this case, you cannot make isolate. Why? Because suppose instead of this HT, with this HT also there is a tile associated, right? Because in every router there is a tile associated like this. This is a tile. So same way here also there will be a tile associated with this. So what about the core inside that tile? What about the L2 bank inside the tile? In maybe it may be possible that this core here, this core request for this L1, and if there is a miss in this L1, then we'll need to go to the home bank of L2. Assume that the home bank is here in this L2. Home bank is here in okay, somehow my mouse is not working. Okay, so home bank is here, suppose home bank is here, so it has to travel through this NI, it has to go here. So in that case, we cannot isolate. In case of TCMP, we cannot. If we isolate, then we have to remove this tile completely. And even not just if we remove the tile, then we are not just disabling a core, we are also disabling a part of the LLC last level cache also. That's why it is challenging. If you want to keep this hardware Trojan alive, so if you want to, if you don't want to isolate it completely, then how to handle it? It's again open area, and you can think about it. Then some more possible attack is HT router can isolate a complete region. Maybe it may be possible that if HT is here, a hardware Trojan is here, then it can isolate this complete region, or maybe this region. So I'm not explaining it in more detail, but it's possible. CCA attack on TCMP having HT router. This is one area where we are currently working now. The covert channel attack on TCMP, where assuming that there is a TCMP where smart detection mechanism for covert channel is already there. Their detection mechanism can detect all the same set covert channel attack and all. Those things are already implemented, but still assuming that there will be one Trojan application, one spy application, and in addition to that, there are some HT routers available in the TCMP. So combining these three, how can we perform covert channel attack where smart detection techniques are already implemented? We are working on this problem. So again, I will not disclose it in more detail. NOC compression based covert channel. This we are at present I'm not working, but there is an interesting problem also possible here, because I'll just give a small idea. Why? Because if you are sending a compressed packet through the NOC, it will take very less time because number of fleet is less. Suppose the data is completely compressible, then in that case you will send only, you need to send only one fleet to send the complete packet. But if your data is completely uncompressible, then you have to send the complete packet, the 16 fleet suppose. So completely uncompressible, long latency, high latency, completely compressible, less latency. Again, there is a time difference. You can use it and maybe propose some more covert channel attack. So I think I'll not go any further. I have to stop here. There are many more. That's why I said millions of attacks possible. That's why I'm saying not maybe actually millions, but at least hundreds of attack is still possible. There are other modules like non-volatile memories, and that case also timing based attacks are possible. But I am stopping here. I hope I have given some ideas to you. So now I'll quickly discuss about the current research that is going on in my lab, efficient static partitioning for CCA, means covert channel attack. As I said, covert channel attack is possible in dynamic partitioning, but if we fix the partition, like if the partition is static, then covert channel is not possible. But I have explained that there is disadvantage of covert channel, static partition. So we are working currently on that, how to use static partitioning efficiently such that we can prevent covert channel attack without degrading the performance. So we are working on it. Then CCA attack based on multiple set which cannot be detected. I think I have already explained it, that we are also working on covert channel attack which can target multiple set instead of one set, such that the existing detection technique cannot detect them easily. NOC HT rotor based attack on top of existing defense technique. Here also we are assuming that if there is an existing defense technique already there in NOC to handle the hardware trojans, then on top of it, how can we propose new attack? Attack based on NOC, non-volatile attack based on non-volatile memories. I have not discussed anything on it, and I think I don't have time, so I'll skip this part. But yes, we are also working on the possible attacks in non-volatile memory based last level memories. Okay. So attack based on recent replacement policy, we are also working on it. Mainly we are working on how we can change the behavior of Hawkeye. Then covert channel attack on DNUCA. I have already explained a possible attack on DNUCA, that how we can migrate and change the access latency. So we are also working on it. And hardware efficient countermeasure for raw hammer attack. So this is a area where I am working from long time, at least from last 1.5 years I am working on it. So raw hammer attack I have discussed in last part. Okay. And lastly, we are also working on proposing covert channel attack on TCMP combining HT rotors. So quickly I will give you 3 classification here, whatever attacks I discussed. First type of attack is here, they are not changing any hardware component. Okay, this is the first attack. They are not changing any hardware component, no hardware change. What are this type of attack? Initially, the attack that I have explained, like covert channel attack, prime probe attack, only misusing the advantage of cache memory, like misusing the properties of cache memory, like miss more delay, hit less delay. So just misusing the existing the current hardware. There is one kind. This is one category. Another category is malicious hardware, right? Hardware trojan means some hardware component are malicious. So in that case, this type of attack means some hardware component are modified. So all the NOC HT based attack that I have explained are false in this category. And then maybe very less work happened in this third category is hybrid. That I think the last work that we are doing is hybrid, means assuming that combining that you are trying to run some malicious application on a TCMP where some malicious hardware is also present. So combining these two things together, how can we do further damage? So there are different types of attacks possible. So as I have mentioned that I have explained I spend very less time on countermeasure. I spend more time on attack. It's not like that I just want to propose new attack, because we are not proposing attack, we're exploring attack. If we explore attack, then we can also do something to prevent it. Okay, so quickly how to start research in this area. Knowing the basics of microarchitecture is very important. So you have to understand all the basic concepts. This can be clear from any textbook or online lectures. Knowing the recent advancement in memory architecture. So for this, at least some advanced level memory architecture knowledge is required. So follow online advanced courses of computer memory, mainly which covers cache, NOC, main memory, non-volatile memories, etc. You can follow any lectures. Maybe as a starting point, you can follow the website of all the speakers that has been participated in this FDP. Okay, and start exploring the security related challenges. Follow the well-known researcher in this area. You can start with all the speakers of this FTP, visit their homepage, and also you can revisit the recorded lecture of this FTP. This will be also very, very helpful if you want to start the initial, at least you want to start working in this area. But the last point is very, very important, implementation. Whatever I have explained, everything, how you will implement it. That's why it's a challenging and time consuming task. After you prepare all these things, if you take 3 months here, you need at least 3 more months here. to prepare, to understand how you will implement. So since I am from a computer science background, I normally use simulators to implement all these things. So either I'll go for full system simulator or trace-based simulator. So full system simulator means you can simulate the entire system, including the time also. So all this attack that I have explained, like time-based attack, CCA, covert channel attack, side channel attack, these are best for these. The best is full system simulator. Either you go with Gem5 or Sniper. So we have experts in our department for Gem5 as well as Sniper also. So you can, if you want some initial help, you can contact with us. Trace driven simulators also, these are actually easy simulator. They have comparatively low code base. So you can either go for any of these trace based simulator. At least some initial attack like replacement policies or performance based attack, not like time based attack. So this performance based attack you can also do with trace driven simulator. But yes, this last part, like understanding simulator, implementing it, it's a time consuming task, but it's a one time job. If you spend 3 months to understand a simulator, then you can use the same simulator for all your remaining works. So yes, this is the last slide, and I hope I have explained you all the important points, how you can start. And so I have also given some starting point. I have explained different possible attacks. You can explore them in more detail. It may be possible that some of the possible attacks that I have discussed may be not possible, because as I said, some of them are not yet experimented by me. I have just assumed it and I've explained it so that you can explore it in more detail. Okay, so thank you. So now I am open for questions. So now, first of all, let me read the question of Dr. Biman. Is it possible to schedule an application in a specific core where the data requires in a nearby bank? Yes, it is possible. I think in Ubuntu also you can assign a particular application to a particular code. There are commands also for this. Based on this command, if you want to assign a particular application to a particular core, you can easily do it. Yes, I think someone has raised hand. Please ask question. Let me see who has raised hand. I cannot see who raised hand. Please ask your question if you have raised hand. Okay, any other questions? I'll be here till 12:15 for answering, for clearing your doubts. I am a EC faculty and I am a systems developer. I am familiar with CAT tools. How can I start in this area? In security of NOC. Dr. Viman, this honestly, if you only start with the NOC part, then I think the simulation code for NOC part is small. Even if you go for full system simulator like Gem5 is huge, but the NOC module that is called Garnet is not, its code base is not very huge. So I think if you have, or if your group has minimum knowledge with C++, then I think you can easily start working in this area. And if you have already knowledge of NOC, then it is very good. Then you will easily understand the code structure of any simulator. So I think I'll advise you first try some full system simulator. Better go with Gem5 because the Garnet part of Gem5 is not very huge. Otherwise, Gem5 is a very huge simulator. And if you only want to check some performance related attack and all, then you can also go with some simulator like trace-based simulator like BookSim, NoxSim. They are trace-based, but maybe they will be enough for performance based attacks. Yeah, NoxSim also you can use. Dr. Kalyan, are you here?
Sir, good morning, sir.
Good morning.
Sir, general query, sir.
Yes.
Is there is any simulator for authentication type? You have mentioned about DOS, right? Performance-based DOS attack. And
Okay.
if you don't want to occur DOS attack, you can go for authentication of a edge device.
Right.
So, do you have any simulators regarding in that line?
I think the authentication part is not implemented in the default version. Means if you download any full system simulator, I think the authentication part is not there, but you can easily implement it. You can just extend that the NOC module to support authentication. I think it is doable, but you have to do it by yourself.
In full system simulator, sir?
In any simulator, I think all the NOC simulator they have an authentication facility, but it can be done. So you can modify the code for this.
Oh, okay, sir. Thank you, sir.
Okay.
So, Dr. Shirshendu, if there are no questions, probably we can close this session.
Yes. Please, we can close.
Okay. Okay. Thank you, everyone. Thank you, Dr. Shirshendu, for sharing details of your own research and giving possible directions. So we are closing this session now. It's 12:15, 12:16. So we will start at 1:15. Okay. And the next session is the last session. We are going to look at some of the security issues at the storage. Thank you. Please come back by 1:15.
Okay, sir. Thank you, sir.